Geometry, Section 10.7, Areas of Circles, Sectors, and Segments of Circles. We have the three formulas on my notes here, and I'll scroll down for you. The three formulas just to kind of set them apart. I've put a red star next to. There are three area formulas in this section. The first one you ought to probably be very familiar with from previous courses, and even we touched on it this year in geometry. The area of a circle is pi r squared. Now, the one thing that I should say about this formula is that you should be careful to not confuse it with the circumference formula. And that is by far the most common mistake that I'll see students make, is a silly one, which is to confuse it with the circumference formula, because they kind of look the same and they have all of the same elements just rearranged. And I'm not going to even say what the circumference formula is, because I don't want you to confuse it or get it in your head right now that there are similarities even, but that they are completely different. And you should understand that, circumference is distance around, whereas area is the area that something occupies. I think of times when I've flown over the Midwest out to the west, like I'm thinking it's probably like the Oklahoma area, and I look down and I see a bunch of square plots with circles in the middle, and I wondered what those were, and I investigated, and what those were agriculture pieces of land, and the source of water is right in the center of the square. And then if you can imagine this, the agriculture, the watering arm that just goes around in a circle. So it makes sense to plant the circle, not the square necessarily, but just the circle. Well, I mean, there's a real example of, how many crops can you plant? How much corn are you going to get? How many soybeans, whatever it is that you're growing? That's an area. Whereas the distance around, if you're to measure the distance that the farthest most point on that irrigation arm would travel in one circle, well, that's a circumference. Okay, so there's a real example of the difference between the two. Anyway, will the homework ask you to calculate just the simple area of a circle, and it's just pi r squared? Yeah, it might, and I could ask that on an assessment too. This one will give you a little bit more of a challenge. This one here says a circular archery target has a 2-foot diameter. It is yellow except for the red bullseye. I tried to draw it here. Red bullseye at the center with a 6-inch diameter. Find the area of the yellow region and round your answer to the nearest whole number. Okay, so I tried to draw it, and I did make a conversion. 2-foot diameter would be a 1-foot radius, which would be a 12-inch radius. I went ahead and changed this to inches because I knew that that the bullseye was already in inches, and its diameter is 6, so I made that radius to be 3. Now, the area of the yellow region, everyone should probably agree, would be the area of the entire circle minus the area of the bullseye. I like to do this type of thing in one calculation. I like to encourage you to do the same thing. Rather than make a calculation, over in one space and it's one circle, and then in a different space make another one, and then bring them together and subtract them to come up with the final answer, it makes more sense to me to just do pi r squared of the big circle minus pi r squared of the small circle, all in one calculation. And yes, I realize that just writing it as the way that I did could be confusing, but what I then would like to do is just give this a little bit of a subscript notation. Okay, so maybe just big and small. Pi r squared, where the r is r sub b, the radius of the big circle, minus pi r squared, where this r is the radius of the small circle. Now you're distinguishing between the two radiuses. Pi times 12 squared, that would be the area of the large circle. We're subtracting pi times 3 squared. And I can't help but show this, 144 pi minus 9 pi, which would be 135 pi. And certainly sometimes we will ask the question where we ask you to leave the answer in terms of pi. If that's what they wanted, the answer would be 135 pi inches squared. They didn't ask for that, though. They did say round to the nearest whole number. So that's where you reach for your calculator. In the previous lesson, I asked you to use the pi button on your calculator and not an estimated value of 3.14 or whatever, right? I don't know how much of that they made you memorize in middle school. Point is that no matter how much you've memorized, the pi button on your calculator is going to even be more accurate than that. So please use the pi button on your calculator, and that comes out to 424.1150082. Since they said nearest whole number, we're going to go with 424 inches squared. Okay, 424 inches squared. The next thing is a sector of a circle. Now, as I show you the definition here, what I would think of is simply a pie slice. And a sector of a circle is a region bounded by an arc and two radii of the circle. So for this drawing, that would be this arc right here that we learned to call this arc AB. And then the two radiuses, radii is plural for that, being the segments AO and BO. This one and this one. This is a segment of a circle. And very much like the length of an arc of a circle, the segment of a circle is a portion of the entire circle. So we need to take a fraction. That's what this calculation is. The area of a sector of segment AOB is a fraction. It's the measure of arc AOB out of 360. It's this much out of 360 times our circle formula, pi r squared. Okay. Now, before we do an example like this, I will point out the way they name the sector is with 3 letters. Please, please don't really confuse that. Be careful not to confuse that with the way we were naming minor arcs, semicircles, and major arcs. This is different. Yes, this does include the center. I really will not make a focus out of naming the sector at all. But it should be not confusing at all when they say sector AOB, and here's AOB. Obviously, we're talking about that sector that I have colored in gray. Okay? So as far as the area goes, the measure of arc AB, that's 2 letters, that's a minor arc, that goes from A to B in the shorter distance along the circle, times pi r squared. Okay, so again, what does that look like as an example? Well, here we have the measure of an angle, an interior angle. That's actually called a central angle. That is 100 degrees. That would mean that the measure of this arc is also 100 degrees. And that means that the area of that shaded region, what they have called sector ACB, right, ACB, would be the measure of arc AB out of 360 times pi r squared, where the r is 6 meters. So that work, and you should show your work on a problem like this, pretty much all the way through chapter 10, you're showing your work. Probably 85-90% of the time they're work problems. 100 out of 360 times pi r, which is 6 squared. Okay. Now we can reduce this fraction if you want. You can type this right into a calculator. Do notice they said leave it in terms of pi, so we should not use the pi button in this case. You could do 100 out of 360 times 36 and get the number. You could simplify this fraction first. That's 10 over 36. That's 5 over 18. 5/18 times 36, and do the math that way. And what you'll end up with looks like it's going to be 10 pi. Meters squared. It's an area. The area of this pie slice, if you will, what's in blue, is 10 pi meters squared. Something significantly less than the area of the entire circle, which would be pi r squared, right? 360 out of 360, pi r squared would give you something bigger, of course. Okay, so 10 pi meters squared. The last thing and the most in-depth thing is what's known as as a segment of a circle. And a segment is defined there as a region bounded by an arc and the segment joining its endpoints. And you might look at that and say, hey, you can't use the word segment in the definition of segment. But you understand that we have 2 different segments now. This is the definition of the segment of a circle. We already have a definition for this segment, right? That segment is a segment that has endpoints x, y. And so it's bound by the arc that is xy, arc xy, that minor arc, and segment xy. By the way, it doesn't have to be a minor arc. Just in my drawing here, it's clearly less than 180 degrees. But it's what's here in gray. It's this little sliver right here. And we have a pretty clever way of calculating the area for this, and that is to take the area of the sector, something we just learned above, all right? So the pie slice that is sector XPY, this calculation, and subtracting the triangle that is this right here. Stop and think about that for a second. If I take the area of this sector, that's too much. It's not just the gray region. But then if I take out this triangle, I'd be left with just the gray region. So it's the area of the sector minus the area of the triangle. Now, if you look in your book for the way they're going to calculate this triangle, you'll see that what they'll have is usually it's a 30, a 45, or a 60 degree angle right here. And you can fit this into a 30, 60, 90 right triangle or a 45, 45, 90 triangle. And what they'll do is they'll draw this line right here and split it and calculate the area that way. I'm not going to teach it that way. Rather, I think that this will fit more problems, kind of be more universal if we just use the 1/2 BC sine of A formula. Okay, that was taught a couple of sections ago. Section 10.5 had area of a triangle is equal to 1/2 BC sine of A. That's the one we're going to use. And then these angles don't have to be anything specific. They don't have to be 30, 45, or 60. They could be 27 or 83. Probably not 83, but they could be anything we want them to be. That being said, on the homework then, there will be a section where they're giving you the exact answers, the book textbook homework I'm talking about, where they give you exact answers in terms of the square root of 2 or the square root of 3, where you're going to have to round, right? Because any problem where we did that triangle formula, the non-traditional one, the side angle side one, 1/2 BC sine of A, you're rounding. And that's what we'll do on this final example, is round. So here's a segment, right? It's bound by the arc that is arc AB and the segment that has endpoints AB, right? Segment AB. This shaded region is what's known as the segment of a circle, okay? And the area of the segment, and I like to do this all in one calculation, is the area of the sector minus the area of the triangle. I'm going to stick an of in here. Area of the segment is equal to the area of the sector minus the area of the triangle. In fact, I even like to do this sometimes too. Little subscript notation like this. Area sub seg is the segment equals the area sub sector minus the area sub triangle like this. That's the calculation we're going to be doing. Okay. Well, we just learned how to do a sector. That's going to be, because this measure would be 120 to match this measure, that's going to be 120 out of 360 pi r, which is given, 24 squared. And then from that, we're going to subtract the area of the triangle, which is 1/2 BC sine of A. Now stop and think about, what are the B and the C? Sine of A, that capital A is going to be the angle 120 degrees. The area of this triangle, forget about the whole circle, forget about the segment for a minute. We're just focusing in on this triangle right here. That angle is 120 degrees, okay? And that would be the capital A in 1/2 BC sine of A. Okay, but what are the B and C then? Well, the B would be this segment here, the C would be this segment here. They're lowercase letters. This is why it's the side angle side formula. The two sides are adjacent to the angle, if you will. Okay, so that happens to be just the same number twice. 24 times 24. 1/2 BC sine of A in this case is 1/2 24 times 24. Now, is it always that? No, we saw other triangle examples where this might be 5, this might be 8, and this might be 7.3. And if I knew, forget about the 8, if I just knew this angle right here were 68 degrees, right, we could use 1/2 BC sine of A, and the B and the C are the 5 and the 7.3, okay? So in this case, since it's the radius of the same circle, though, this is also a 24. Therefore, these two numbers are the same thing, and then that's just the sine of 120. Now, you can, at this point, you can just type that into your calculator, okay? Carefully. Obviously, it's a long keystroke. You can carefully type that in. I do like to simplify things just a little bit. That's just to my own liking. So this does come out to 192 pi. That's an area of the sector, okay? And then 1/2 of 24 times 24 is 288. Sine of 120. And then I find that just to be easier to plug into the calculator. That's not a requirement. Just do it right. Don't sacrifice a line of work for accuracy. But if you can type this right here into your calculator, great. you should get 353.8. 353.8. Let me write that again. Nothing works the way you want it to. Feet squared. Okay, so again, 3 concepts were covered there. Area of a circle should be easy. Area of a sector is just a fraction of the circle formula. And then this one, which is again the most in-depth one, which is the area of a sector minus the area of the triangle, which gives you that area of a segment. Thank you for tuning in.